Another component that's been identified as being a significant mechanism in terms of, if you will, impaired selective attention in older adults is general cognitive slowing. And one of the ways that the speed of selective attention has been studied and quantified extensively in experimental psychology is through an experimental technique that we can refer to as the Treisman visual search paradigm. It's named after a famous cognitive scientist named Anne Treisman, who developed this approach. And what Treisman identified was that there are two very different types of visual search that can occur, and that these two different types of visual search can be, if you will, distinguished by the slope of their search function. And what we see here on the right is the plot of two search functions. What we see on the x-axis is how many distractors there are up on the screen that you're searching. And what we see on the y-axis is how long did it take you to find the target. And what we typically see in one type of search, a very special type of search that's called parallel search, is that no matter how many distractors we have, our search is pretty fast. And we don't really slow down very much as we go from 2 distractors to 10 distractors to 40 distractors, so to speak. And that's called parallel search, and we'll consider that in more detail in just a moment. So that's one type of a search. There's a second type of search, though, that's what Anne Treisman referred to as serial search instead of parallel search. And in serial search, what we see is every time we add a distractor, we get slower and we get slower and slower and slower in terms of the time it takes us to find the target. It's as if we have to process every single stimulus as we're searching through the array one by one, processing the distractors until finally, aha, we look at the stimulus. So if you have a steep slope like this in your search function, that suggests that you are doing a serial search task. And if you have a flat slope, as we're seeing in this bottom example, you are performing your search using a parallel approach as opposed to a serial approach. So what we need to do at this point is let's take a look at, if you will, some examples of what if you will, a fast search might look like, what the stimuli might look like in a fast search, and what the stimuli might look like in a slower serial type of search.
Okay, so what we're going to do first here is a pop-out search. And the target we're going to be looking for is a green letter O, right? So what's going to happen is you'll be presented with an array of stimuli on the screen, and you have to answer yes, the target is present, the green letter O, or no, there's no target present. And on each trial, the number of stimuli in the display set will change. So let's see what this pop-out type of search looks like. All right, my fingers are on the appropriate buttons, so let's start. Oh, there's the target. No target. No target. Target popped right out. No target. No target. Target popped right out. So you could see what happens here is when we have a green target against blue background, there's no overlap in the perceptual color space. What happens is the green target pops right out and we can immediately localize it no matter how many distractors there are. So now let's take a look at a search that is a little bit more difficult. And what we're going to do here is we're going to look for the same letter O, same green letter O, but now the background targets, the distractors, sometimes those will be green, sometimes they'll be blue. So we no longer have this nice distinctive perceptual dichotomy between the target and the distractors. So it becomes an effortful cognitive search that's serial in nature rather than parallel. So again, we're looking for what? We're looking for the green letter O. And here we go. Ready? Up, there's a target. There's a target. No target that time. Not quite as easy to do this test. No target that time. Yeah, there's a target right in the middle of the screen. No target. So that took me a long time to do that search. And there's a target way up on the left. And no target. So we should experience this as being more effortful and taking a longer time. No target. There's a target. No target. So you can see this is a more effortful type of search.
So now that we've seen the examples of the two different types of search paradigms that Treisman identified, let's talk a little bit more about each one in turn and explore their primary characteristics. First, let's consider the fast, efficient, parallel visual search. That was the case where no matter how many distractors you added, search time didn't really appear to slow down. And this occurs in the special case where the distractors in the paradigm, the distracting stimuli, all share a common perceptual property. And the target, on the other hand, is characterized by a different level of the same perceptual property. So, for example, if all the distractors were blue and the target was green, there'd be a clear perceptual distinction between the target class and the distractor class. Similarly, the distractors could all be, let's say, vertical lines, and you might be searching for a target that's a horizontal line. In that case, you'll see a pop out because of the difference in orientation. All the distractors are one orientation, the target's a different orientation. And in these cases where the stimulus can easily be found no matter how many distractors occur, was described by Treisman as being a pop-out effect, because it's as if the stimulus pops right out of the display. You can't help but see it. And it's as if one is processing all the stimuli simultaneously. And that's why it's called parallel search. Interestingly, the perceptual dimensions where such pop out occurs tend to be the same dimensions that the cells in the visual cortex are specialized to process. For example, cells in the visual cortex are specialized to see one of a family of orientations, or specialized to see a particular color, or specialized, if you will, to see a particular orientation or size of a line. You see on the screen here an example of a pop out if the distractors were all black X's and the target was a red X. Based on that color discrimination capability that could be done at low level perceptual information processing instead of requiring higher level cognitive processes, we see this very fast, efficient parallel search. But what about slow, effortful serial visual search? And what Treisman theorized was that most of the objects that we search for in day-to-day life are objects that are defined by multiple properties of perceptual, if you will, categories. So, for example, we rarely search for something that's red against distractors that are all blue. Instead, we typically might search for the blue shoe, or if you will, the small marble. And in these situations where the target is defined by multiple properties, then essentially search is slow and effortful because attention is required to bind those different properties together into what you could refer to as cognitive objects. So when we're searching for things, most of the time, we can only search for or evaluate one or two of the items in the visual world at a time. And we have to sequentially and slowly go through each of the items in our visual field as we search for the target, comparing each item to the, if you will, the template we hold in our head that we're searching for. So since attention is a very limited commodity, we can only proceed at a very slow pace. At least that's the theory that Treisman put forth. So here's an example of a conjunction search, searching for stimuli that consist of multiple properties instead of just one. Here we're looking for a letter N among M's, and would be a case where our display size is 6. And now we have display size of 49 here, and finding the N in this case takes much longer. And what we would typically find is the more distractors there are, the slower we would be. And we would typically get the signature for a slow serial search. So now, finally, after talking about all this, type of search theory within the Treisman context, we get to the money slide. That is, what are the age differences that we observe in these types of searches? Well, what we find is that serial search processes, which are depicted by these processes with the, if you will, the steep slopes, tend to slow down as we grow older. In this case, for example, we see typically young people in the search paradigm might take 17 milliseconds longer for every distractor that's added, whereas in the case of older people, they take 23 milliseconds longer for every item that's added. And that's a 35%, if you will, slowing in processing speed in the case of the older adults. Interestingly, we don't observe a difference in the slope for old versus young people when we do pop-out searches. So the problems we saw in search beginning back in Patrick Rabbit's study seem to not involve perceptual difficulties, but instead seem to involve a slowing at the cognitive processing level that is higher up in the ultimate stream of processing. And there's just one more note that I would like to mention while we're on the topic of, if you will, visual search using the Treisman paradigm. And that is some really important research has been done over the last few decades showing that one can train visual search skills, and in fact many other visual search skills, to become more and more efficient if the training is done in a consistent fashion. So for example, if we search for, let's say, letter K, and the distractor is always either an M or a J. I'm just using this as a made-up example. But if the distractors are always the same and the distractors never serve as a target, and we now practice many thousands of trials, what we find is we start out with the classic effortful serial search slope in our search function, as we see here in this dark black line. But look what happens to the search function as we do 1,000 trials, and then 2,000, and then 3,000, and 4,000, and 5,000. As we work on this task over and over and over again, we develop visual skills. And that's called an automaticity of a task, where it changes from being a slow serial cognitive process to a faster, more efficient process that begins to approximate what we referred to earlier as parallel processing. And this automation of visual skills is quite an active area of research. But what's remarkable is when people have tried to do this with older folks, healthy older community residents, what researchers have consistently found is that it is nearly impossible to see this bending of the search curve in older adults. That is, they don't develop automaticity. And that's something we need to keep in the back of our mind when we're going to talk about some other processes in the future with respect to, let's say, memory processes and learning processes.